We are nearing the end, and so I will remind you of two hearts that we had on the board. One was we love orthonormal bases, and the other we love diagonal matrices. So it's a very natural question to ask, especially in light of what we have just done in the most recent videos, for which n by n matrices, or which n by n matrices have an orthonormal eigenbasis. Now let's just restate that. Let's unravel what this is really saying. Equivalently, for which n by n matrices A can we find an orthogonal matrix S and diagonal matrix D such that S inverse AS is this diagonal. And another way that we can write this, so maybe I'll put this in parentheses, recall, let's say S is n by n is orthogonal if and only if S transpose is S inverse. And so we can rewrite this is equivalent to S transpose A, S is D. Okay. So this is the question. Which n by n matrices A have this property? Note, A, the matrix A, is said to be orthogonally diagonalizable. And this matrix S, well, we know the columns of this matrix S are an orthonormal basis for our n. That's just because it's n by n orthogonal matrix. So this is a very interesting question, and I have room on the board here to give you the answer, although the answer is already on the board in a sense. But the answer is called the spectral theorem, which we will not prove, but I'm going to mention parts of it. It's called the spectral theorem. It's a very fundamental theorem in linear algebra. It says a matrix A is orthogonally diagonalizable if and only if A is symmetric. And this means that A transpose equals A. Okay? So these are precisely the matrices that are orthogonally diagonalizable. Or another way to say that is you have an orthonormal eigenbasis precisely, well, for a matrix, precisely when that matrix is symmetric. So maybe I should write this as the answer to the question here. Okay, let's discuss a few important properties about symmetric matrices that really go into the spectral theorem being true. Okay, so here, if A is an n by n symmetric matrix, then, well, the first one that I'll mention is that A has n real eigenvalues, and this is if you count with algebraic multiplicity. Okay, and this number 1 I will not prove, in part because we never talked about complex eigenvalues, and that sort of goes into the proof of this, but this is definitely the case. But the second one I will prove. It's a nice exercise, and that's the following. If A is an n by n symmetric matrix, then for lambda 1 not equal to lambda 2 eigenvalues of A with V1 and V2 associated eigenvectors, we have that V1 dot V2 is 0. So what this says is, if you have eigenvectors corresponding to different eigenvalues of a symmetric matrix, they are perpendicular, right? This is what this says. And I mean that V1 corresponds with lambda 1 and V2 corresponds with lambda 2, like this. So if you have eigenvectors corresponding to different eigenvalues, they are perpendicular. So let's prove 2. It's really just a trick. It takes a little trick to realize this. We'll do it in blue. So let's assume A is symmetric, and that V1, V2 not equal to 0, with AV1 is lambda 1, V1, AV2 is lambda 2, V2, and lambda 1 not equal to lambda 2. So in my assumptions, right, A is symmetric, V1, V2 are eigenvectors corresponding to different eigenvalues. And we want to show V1 dot V2 is 0. In fact, we will show this V1 transpose V2. Remember, this was a way to write the dot product in terms of what looked like a matrix product. We will show this is 0, and we will use that A transpose is A. This is the definition of symmetric. Lambda 1 times this dot product. Well, this is a scalar times, as I've written it, a matrix product. I am just going to pull the scalar into the first one. So this would be lambda 1 V1 transpose, parentheses this way, V2. Now V1 is an eigenvector for A with eigenvalue lambda 1. So this is, maybe I should go down. This is A V1 transpose V2. But now I can use a property of, if you have, you can think about this as matrix times matrix. Transpose, this would be V1 transpose times A transpose, property of transposes. So this would be V1 transpose A transpose V2. And then A transpose is A. AV2 is, forgot my transpose. AV2 is lambda 2 V2. So this is, maybe I'm going to have to move over here. This is V1 transpose lambda 2 V2. And finally, I can pull the scalar out in front, and I'll do this right down here. It's lambda 2 V1 transpose V2. Okay. Now, let me put a little line because I'm going to use over here. Okay, so look what we see. we see lambda 1 v1 transpose v2 is equal to lambda 2 v1 transpose v2. I can just subtract, let's say this minus this would be 0. So then we have lambda 1 minus lambda 2 all times v1 transpose v2 is 0. Okay? Like I said, I take this minus this, and then I factor out this v1 transpose v2. But you see, lambda 1 is not equal to lambda 2, so this part is not equal to 0, and I can conclude that this is 0, as lambda 1 not equal to lambda 2, we see v1 transpose v2 is 0. And this is exactly what I wanted to show. So we have proved this part, that when you have distinct eigenvalues, their associated eigenvectors are perpendicular for a symmetric matrix. I'm going to make this comment, and then we will do a bunch of examples, then I'll make some more comments. But this spectral theorem, it says the following, that A is symmetric if and only if there is an orthogonal matrix S with S transpose AS is D diagonal. Okay, I have just kind of rewritten, but let's unravel this a little bit. Okay. Equivalently, what do we see here? We see that AS equals SD. That's just multiplying by S on the left of both sides of the equation. Meaning, I'm going to solve for A here. Now I multiply on this side. A is SD S transpose. So what this says is that. So what this says, maybe I'll get, okay, I have a new color here, this pink. What this says is that every symmetric matrix, and this is my comment here after I unraveled a little bit about the spectral theorem, it says every symmetric matrix is of the form SD S transpose, where S is n by n orthogonal. Oops, I misspelled it. Meaning the columns of S form an orthonormal basis for Rn, and D is diagonal. Uh-oh. D is diagonal. Now what I'd like to do is let's just check that this in fact is symmetric. So what I want to do is take the transpose of this, and I should get back that again. So here we go. I take S, D, S, transpose, transpose. Well, just like we saw in the proof that I did about eigenvectors of a symmetric matrix, well, what I used is if you have to take the transpose of a product, you have the product of the transposes, but it's in you switch the order. Okay, so here, this would be, well, it would be S transpose, transpose, D transpose, S transpose. And now let's think, well, any matrix n by n, or even just general, any matrix, you take the transpose, then you take the transpose again, you get back your original matrix. Now, this is diagonal. Diagonal matrices, they're symmetric. So D transpose is D, and then we see S transpose. So in fact, anything of this form is definitely symmetric. That was just a nice exercise. Okay, now let's get to some examples, and then we will make some more comments. Here's our first example. I'm going to do 1 2 by 2, 1 3 by 3, and then 1 4 by 4. This is how we will proceed. And this one's 2 by 2. Okay, we see a symmetric matrix. We want to find eigenvalues and an orthonormal eigenbasis. Okay, well, what we need to start off is this. Well, just as a comment, maybe let me say this before I write. Look, the row 2 is 2 times row 1. This matrix is not invertible. We will see 0 is an eigenvalue. We see that before we even start writing anything down. But let's do this so we can find the other one. So we have 1 minus lambda, 2, 2, 4 minus lambda. Okay. Then we multiply. Let's see. We have lambda squared. We have minus 4 lambda minus 1 lambda. Then we have plus 4 minus 4. Okay, so we see here we have the characteristic polynomial lambda squared minus 5 lambda, which factors. We see the eigenvalues here. We have 0 as we predicted, and we have 5. Okay, now I need to find a minus 0I is just this, and then we will have a minus 5I here. Okay. Here we get that, let's see, x1 is minus 2x2, where x2 is a free variable. One vector in here would be, for example, 1 minus 2. But this is not, we're trying to find an orthonormal eigenbasis, and this is not unit. So that would be our final step here. This has length, this 1 plus 4, 5, square root of 5. Okay, so the unit here okay, this is for, okay, and then, oh, same color. Now I need a minus 5I. This will be minus 4, 2, 2, minus 1. And this I can just do one step, really. We see that this row is a multiple of this row. So I can put zeros here, and then here will be a 1, negative half. x2 is free. We see x1 is 1/2 x2. It will look like this. 1, 2. Again, it's not unit, but uh-oh. I did it backwards. If this is going to be 2 and 1, you know how I realized it? And this is why I always say check your work, because I was about to say, but we can take the dot product of these two vectors and realize we get 0. And when I had 2 and 1, it was not the case. But now it actually makes sense for this equation. If this is 2 2 times a half is 1. And if you take this vector and take their dot product, you get 0. And that's something that we proved, right? We have 2 different eigenvalues. Lambda is 0, lambda is 5. These 2 eigenvectors will be perpendicular for this symmetric matrix. Okay, but then I need the corresponding unit vector, and I get 1 over square root of 5, 2 over square root of 5. This corresponds to lambda is 5. And so, well, I have everything here. My orthonormal eigenbasis, I will just write it here. Like this, okay? This was for this 2 by 2 matrix. Okay, well, we had the exact same instructions. We have a 3 by 3. But again, look, column 2 and column 3 are the same for this matrix A. And so we should expect 0 to be one of the eigenvalues. Okay, well, let's compute. We notice it's symmetric, right? That's like step 0 in one of these problems. If I wrote some matrix that was not symmetric and had this, well, we wouldn't be able to do it because of the spectral theorem. Okay. Determinant A minus lambda I. We have 2 minus lambda, 2, 2, 2, 2, minus lambda, 0. 0 minus lambda. Well, we have some choices. I might as well expand about this column. I could have equally just done the bottom row. I have a 0 in each one of those, which gives me a few less steps. So I have plus, minus, plus, and then I have the determinant where I cross off here. So it's 2 minus lambda, 2, 0. Okay, so it's plus, minus, plus, but it's a negative lambda. And now I do this, and I get 2 minus lambda, 2, 2, and minus lambda. Lambda, 2, 2, minus lambda. Okay, so I have a 2. And then I have times 2 lambda, minus lambda. And then this one, we get a minus lambda, 2 minus lambda, minus 4. Let's see, maybe I will multiply this out just a little bit. Come over here. We have 4 lambda as the first term, and then we have minus lambda. This is lambda squared minus 2 lambda, and then we still have the minus 4. Okay, one step at a time. We actually almost have this. Now all I have to do is distribute the minus lambda, and we will be done here. So I'm going to have a minus lambda cubed. Well, refactor, of course. Then I'm going to have a plus 2 lambda squared. Okay. And then I will have a plus 4 lambda. And here's another 4 lambda. It will be a plus 8 lambda. Now, typically, factoring a cubic is challenging, except you notice every single term has a lambda. In fact, I'm going to pull out a minus lambda just to make my life a little easier. I have lambda squared minus 2 lambda minus 8. And now how does this factor? 4 and 2, right? Minus lambda. And then I have lambda minus 4. I'll check it just to make sure. And lambda plus 2. These multiply to -8 and add to -2. Okay, wonderful. So let's just remind ourselves. I'll put them up here. We have lambda is 0, 4, and -2. These are eigenvalues. Okay, so let's work with one of them since I do still have space on the board. This is for lambda equals 0. A minus 0i is just a. So I need to find something non-zero in the kernel of this matrix. Okay. Well, I'm going to take 2 steps, or maybe actually 3 steps at once. Convince yourself, you should, that I can get myself here. Uh-oh, I'm going to put a 0. Okay. And then I really only have one more thing to do to be in reduced row echelon form, which is this. Okay. That's not that hard to get yourself from here to here, especially at this point in the semester. Okay, now, with this reduced row echelon form, look what we see. We see x1 is 0. We see x2 is negative x3. And so one vector would be 1, minus 1, 0. But it's not unit. And so a unit vector, because I'm looking for an orthonormal eigenbasis, well, this vector has length square root of 2. So a unit would be 0 minus 1 over square root 2 and 1 over square root 2. Okay? Oh. And this corresponds to the eigenvalue lambda equals 0. So I'm going to erase now, but I'm going to keep this on the board, my eigenvalues on the board, and then I will work with lambda equals 4 and lambda equals -2. Okay, now for lambda equals 4, what I'm looking at is a minus 4i. This becomes -2, 2, 2, 2, minus 4, 0, and 2, 0, minus 4. Okay, what can we do to this? Well, the first thing I will do, let's see if I can do a few steps at once here. Here's one intermediate step, and then for example, if we do one more, so I'm doing multiple steps in one here, and you should fill in the details if you don't see how I get from one to the next with elementary row operations. So what would be another one I could do here? Okay, here's reduced row echelon form. Well, what do we see? We see that x3 is free. We see x2 is x3. We see x1 is 2x3. And so one vector here would be, let's say 1, 2, 1. This has length, let's see, 4 plus 1, square root of 6. It's not unit, and so maybe I will write this above. I'll do it in black. This e sub 4, because this was lambda equals 4, is the span. Now I'll make it unit. 2 over the square root of 6, 1 over the square root of 6, 1 over square root of 6. Okay, now we just have one more, which is for lambda is -2. I'll use this black again. What I need is a plus 2i, which is 4, 2, 2, 2, 2, 0, 2, 0, 2. And again, let's try to go through this row reduction by doing a few steps at once. What's one thing I can see here? Well, here is one intermediate step, and then let's see if I do another one. This one I'll just try to eliminate this 1 and this 4, turn them into 0, and then I might be able to work from there. So I have 1, 0, 1. I have 0, 1, minus 1, and then I have 0, 2, minus 2. Oh, okay, great. In fact, maybe I'll just stop here because of course I could take one more step and turn this bottom row into all zeros, but we can read off what I need to from this matrix, because this first part, the first, say, 2 rows is what we would see in the reduced row echelon form. So we see that x1 is negative x3. We see x2 is x3, and we see x3 is free. And so we would get, for example, 1, 1, minus 1. And this has length square root of 3. And so maybe I need to write this below. This is for lambda equals minus 2, that e minus 2 is the span of this unit vector. Minus 1 over square root 3, 1 over square root 3, and 1 over square root 3. Okay, so to finish this problem, although I will make a comment about the diagonalization part, but to finish this problem, the orthonormal eigenbasis, which we were asked for, is 0, negative 1 over square root 2, 1 over square root 2. And then the second element I will list is corresponding to the eigenvalue 4. We get this. Those are all positive. 1 over square root 6 and 1 over square root 6. And then the third one corresponds to lambda is minus 2. It's right here. Negative 1 over square root 3, 1 over square root 3, and 1 over square root 3. Okay, now, they're all unit. I made them that way by dividing by their length. And then you can check, take this dotted with this. You get minus and plus of the same thing. Take this dotted with this. You get minus and plus of the same thing. And finally, take this one and this one, their dot product. This would be minus 2 plus 1 of the same thing. They are an orthonormal basis for R3. So this is an orthonormal eigenbasis. Now, we weren't asked in this problem, but we could be about the matrix S and the matrix D. So maybe I will just mention them here, and then we will move on to a 4x4. But you will find, or we will see, the 4x4 I'm going to do actually takes less work than this 3x3. Okay, it's a fun one. Okay, so if we were asked, I'll just say notice or note this S matrix. I just put these here as columns. And D, remember this from when we were diagonalizing in the eigenvalues and eigenvectors video? Well, the eigenvalues go along the diagonal in the appropriate order. So this one corresponded to 0. This will go here. This one we see corresponded to lambda equals 4. And this one corresponded to lambda equals minus 2. So with this S and this D, these satisfy Well, it was that S transpose AS is D. And you could check that if you wanted to. Okay, now for 4x4. Here is the 4x4 example we will do, and then we will make some observations. You see, well, this matrix looks almost like the identity, except instead of ones down this diagonal, they're down this one. Okay, it's not the identity. Okay, well, let's begin with determinant A minus lambda I, which is this. We have minus lambda, minus lambda, minus lambda, minus lambda, then 0, 0, 1. Like this. Okay. I don't know that it makes a difference really how you expand this with cofactors, because it appears that every row and every column has 2 zeros. So I might as well just do the first row, but you could really choose. So I will expand about the first row. I have minus lambda. This is a nice exercise in a determinant of a 4x4 that's not too many steps and too hard to manage. So then I have this 3x3 minus lambda, 1, 0, 1 minus lambda, 0, 0, 0 minus lambda. And then, so this is plus, minus, plus, it'll be minus 1. And then I will have another 3x3 determinant. It's going to be down here, this 3x3. 0 minus lambda 1, 0, 1 minus lambda, and then 1, 0, 0. Now, you notice both of these, this 3x3 and this 3x3 have, well, for example, one column or one row that has only one non-zero entry. So I can pretty quickly evaluate each of these determinants. I get minus lambda, so I will expand here, say about this row, and similarly here, I will expand about this row. Okay, so this will be plus, minus, plus, minus, plus. I have another minus lambda. And then I have just this 2x2 determinant, which is lambda squared minus 1. Okay? And then there's a minus 1. Okay, I have plus, minus, plus. It's going to be times 1. And then I have this 2x2, which is lambda squared minus 1. Well, both of these terms, you see we have lambda squared minus 1, lambda squared minus 1. I can factor out a lambda squared minus 1. The first term, I have a minus lambda times a minus lambda, which is a lambda squared. The second term, I have minus 1. And now, well, each of these is the same thing. It's lambda plus 1 times lambda minus 1. It's going to be lambda minus 1 squared, lambda plus 1 squared. So we have two eigenvalues. And this is an interesting one because here we have lambda is 1 and minus 1, and each have algebraic multiplicity 2. Okay? Well, let's find this eigenspace, or I should say a basis for, in fact, an orthonormal basis for the eigenspace E minus 1, and an orthonormal basis for the eigenspace E plus 1, and then put them together and we will have an orthonormal eigenbasis. We will be able to find the matrix S and the matrix D. Okay, maybe let me erase this so I can use the space. Well, first let's see, maybe lambda is minus 1. This would be A minus lambda I would be A plus I. So we get this matrix like this. And we can, let's see, I'll just take one step here. You can take minus row 1 added to row 4 and minus row 2 added to row 3. And immediately we are in reduced row echelon form. Like this. We see x3, x4 are free. And we see that x1 is negative x4, x2 is negative x3. So we can find two elements in the eigenspace for lambda is -1 pretty easily, or I should say two basis elements. Here we can just take 1, 0, 0, -1, and then 0, 1, -1, 0. But these are not unit. One nice thing, look, before I normalize, these two are perpendicular. So I don't have to do any work to find two perpendicular vectors in the eigenspace for -1. These are already perpendicular, but I will make them unit. So the unit vectors, these both have length square root of 2. We get -1 over square root 2, 0, 0, 1 over square root 2. And then 0, -1 over square root 2, 1 over square root 2, 0. Okay. Now we move on and let's work with lambda is +1, the other eigenvalue. We take A minus lambda I. We have -1s on the diagonal. And then 1. Like this. These are both very pretty matrices. Okay. Well, again, we can, in this one, we can just take row 1, add it to row 4, row 2, add it to row 3. Well, then, so that I have leading 1s and not leading -1s, I can multiply row 1 and row 2 by -1. I will do this all in one step. As I have been doing in this video, I take a few steps at once in the row operations. And then I will have 2 rows of zeros. Now this is reduced row echelon form. Again, we see x3, x4 are free. And we see that x1 equals x4, x2 equals x3. Initially, we could choose, for instance, 1, 0, 0, 1 and 0, 1, 1, 0 as being two elements in a basis for this E sub 1. And just like up here, we notice that these are already perpendicular. So to get the unit ones, these both have length square root of 2. We can just take 1 over square root 2, 0, 0, 1 over square root 2, and then 0, 1 over square root 2, 1 over square root 2, 0. Okay. Very nice. Well, these two are an orthonormal basis for the eigenspace E minus 1. These two are an orthonormal basis for the eigenspace E1. Okay, to get an orthonormal eigenbasis, we just concatenate, put them together. Now, the way this reads, we specifically want the S and we want the D. So let's write those down now, and then we will make some comments Okay, I'll erase all of this. Uh-oh. Okay, so my matrix S is here, negative 1 over square root 2, 0, 0, 1 over square root 2, 0, negative 1 over square root 2, 1 over square root 2, 0, and then we put this one. Then my diagonal matrix, as we have seen in other examples, these two corresponded to lambda is, oh, it's not written. I erased too much. These two were for lambda is -1, these two were lambda is +1, and that tells us how to fill in D. This will be -1, -1, 1, 1, like this. Okay. Now for some important theoretical comments. The first, so all of these stem from this example, but then I'll make some comments generally. In this example, we had that the algebraic multiplicity of 1 is 2, and this was also the geometric multiplicity of 1. And the algebraic multiplicity of -1 was 2, and this is also the geometric multiplicity of -1. And this holds in general. Maybe I'll do that in another color. This is generally true if A is symmetric. And lambda is an eigenvalue of A. I think I'm blocking what I'm writing. That the algebraic multiplicity of lambda equals the geometric multiplicity of lambda. It's definitely not true for any n by n matrix, but for the symmetric ones, where this is, well, as we mentioned, spectral theorem, that's equivalent to being orthogonally diagonalizable. This holds for symmetric matrices, that for any eigenvalue, its algebraic multiplicity, which comes from the characteristic polynomial, is equal to the geometric multiplicity, which comes from the dimension of its eigenspace. Okay, now what else do I have to say? Well, also, in this example, the matrix A, which, let me remind you, it was like this. I'll write it really little. This matrix, well, look, this matrix is, of course, it's symmetric. That's everything we're doing today, but it's also orthogonal in and of itself. The columns are the exact same columns of the identity, right? Which they're just in another order. So these are all unit, the columns, and they are perpendicular. So these columns are an orthonormal basis for Rn. When you have this, so we know some things. In fact, I didn't need to calculate determinant A minus lambda I, and that's my comment here. Let me do this part in blue. So when A is symmetric, we know that the eigenvalues are all real, and we have n of them counted with multiplicity. So suppose we have AV equals lambda V. Okay, where V is not equal to 0. That means that V is an eigenvector corresponding to eigenvalue lambda. Okay, well now let's add. So I'm in this comment number 2. I'm talking what happens when you have symmetric and orthogonal. Symmetric just gives me that I have lambda, they're real. But then a orthogonal, what do we know about orthogonal matrices? They preserve length. In fact, this was the definition. So this says that the length of lambda v, which is the length of AV, well, A is orthogonal. This will be equal to the length of V. Okay, but then one thing I could do here, we know property of scalar times vector, the length of lambda V is absolute value lambda times the length of V. Maybe I'll start a new sentence. So we obtain where the length of V is non-zero, meaning absolute value of lambda is 1. So this is my comment, I'll star it, the only possible eigenvalues for a symmetric orthogonal matrix are +1 and -1. Okay, it's the only possible ones. And we would have known, for instance, that this matrix had to have them both, because if you take, for instance, this -1, you don't get the 0 matrix. That would be the only possibility if you did not have -1 as an eigenvalue, because that would say, for example, that 1 came with multiplicity 4, and so a minus 1 times I would have that rank 0, and it doesn't. So just using this, as I mentioned, well, now that we've discussed it, I wouldn't have to calculate the characteristic polynomial of this. I would know it has 1 and -1 as eigenvalues. But this is a nice observation that we see when you have both symmetric and orthogonal. Okay. What else do I want to say? Okay, number 3. In this example, when we solved for the eigenspaces, or for a basis for the eigenspace, the way my A minus lambda I was set up, it naturally gave me 2 vectors that were orthogonal, and I just had to normalize them. But we can also, if needed, we can use Gram-Schmidt. To find an orthonormal basis for each eigenspace. And then concatenate them. You have an orthonormal basis, well, for Rn, or an orthonormal eigenbasis when you have a symmetric matrix. Now the final comment I'll make is an observation, but I guess all of these kind of are, and that's the following. This is something I've been meaning to say, talking about diagonalization, and I'll say it now, is that diagonalizability and invertibility are different. They're not the same, and one doesn't imply the other. For example, just today we saw a 2 by 2 and a 3 by 3 that were not invertible. It says 0 is an eigenvalue. They're both symmetric matrices. They're both orthogonally diagonalizable. This example is invertible. symmetric matrix, orthogonally diagonalizable. And you can come up with invertible matrices that are not diagonalizable, or not invertible matrices that are not diagonalizable. So when you're thinking in your mind the concepts of diagonalizability and invertibility, they're not the same concept, okay? I wanted to make that comment at some point, so now is a good time.